Right now, I mean, literally right this second, beneath the Atlantic Ocean, there are these pulses of invisible light firing millions of times per second.
Yeah, racing through these hair-thin glass cables just to bring this very audio to your ears.
Exactly. And without degrading it all, we just treat it as a mundane utility, Like we rely on the exact same technology to scan our groceries, entertain our cats, and perform delicate eye surgery.
Oh, totally. And what's wild is that what we treat as this simple, everyday tool actually relies on a bizarre, mind-bending quirk of quantum physics.
Right, something Albert Einstein predicted over a century ago.
Oh, exactly.
So today, our mission for this deep dive is to take a word you toss around casually every single day and unpack the beautiful science hiding right inside it. That word is laser.
We stick it on razors to sound futuristic, but we easily forget it's actually an acronym.
Yeah, you really do. Okay, let's unpack this. It stands for light amplification by stimulated emission of radiation.
Which is quite the mouthful.
It really is.
I mean, the moment you string those words together, it sounds incredibly intimidating, like the title of a graduate-level physics thesis.
Yeah.
But we are going to walk through exactly what that means at an unhurried, comfortable pace. You do not need any kind of science or engineering background to follow along today. By the time we finish, the mechanics behind that acronym will make complete, intuitive sense.
Well, I am definitely holding you to that.
Yeah.
Because light amplification by stimulated emission of radiation feels like a lot to chew on.
It does, yeah.
So logically, to understand why we would ever need to amplify light through this specific process, we probably first need to understand the default state of things, right?
Right.
The everyday light around us, like the light bouncing off the walls right now, is actually quite messy, isn't it?
Oh, it is completely chaotic. We really need to look at the anatomy of ordinary light to appreciate the contrast.
Okay.
Because when you look at the light radiating from, say, a standard lamp in your room or just the sunlight streaming through your window, your eyes perceive it as smooth, continuous, and white.
Yeah, it looks perfectly clean.
But on a physical level, it is a tremendous jumble. Ordinary white light contains many different colors all mixed together.
Like a big soup.
Exactly. And when physicists talk about those different colors, what they're actually describing are different wavelengths. Light travels in tiny waves, cresting and dipping.
Right.
And a wavelength is literally just the physical distance between the peaks of those microscopic waves.
So our brains just interpret those different physical distances between the wave crests as different colors.
That's it, yeah.
Like red has a wider gap between peaks, blue has a shorter gap, and the white light from my lamp is just a massive mashup of all those different gaps and colors smashed together.
That is the perfect way to look at it. You have all these different wavelengths layered over each other.
Okay, got it.
Furthermore, those waves are completely out of step. Like one wave is cresting while another is dipping at total random.
Oh, so there's no rhythm to it.
None at all.
Yeah.
And to make matters even more disorganized, the light is spraying out in every conceivable direction. It spreads out from the bulb, fanning wider and wider, which means the energy weakens drastically the further it travels.
It's like being in a noisy, milling crowd at a train station during rush hour.
Yes.
There is a ton of collective energy in that room, but there is zero coordination. Everyone's walking in different directions at different speeds, just bumping into each other to catch different trains. The energy is totally diffuse.
Exactly. And what's fascinating here is that if ordinary light is your chaotic train station crowd, laser light is a highly disciplined army marching in perfect, synchronized formation.
Oh, wow. Okay.
A laser strips away all that chaos because it possesses three very specific, unique qualities.
And what are those?
First, instead of that mashup of different colors, a laser is monochromatic.
Mono meaning one.
Right. It is a single, pure color, just one specific wavelength.
So we've cleared out the train station. We only have one specific type of person walking at one specific speed.
Second, all of those light waves are perfectly in step with one another. They crest and dip in absolute lockstep.
Okay.
The scientific term for this state is being coherent. When light is coherent, the peaks of the waves align perfectly, reinforcing each other rather than canceling each other out.
Coherent, meaning they are moving as one unified, synchronized entity.
You've got it. And third, because the light is coherent and single-colored, it travels in a tight, extremely narrow beam that barely spreads.
Unlike the lamp spraying everywhere.
Exactly. A normal flashlight beam spreads out and fades into shadows after a few dozen feet. A specialized laser beam, though, can maintain a tight enough focus to shoot across an entire room or even carry its energy all the way to reflectors placed on the moon by Apollo astronauts.
Wait, really? To the moon?
Yeah. Without fanning out into uselessness, that marching army coordination is the entire secret to its power.
But organizing a chaotic crowd of millions of people into a disciplined marching army sounds like a complete logistical nightmare.
It really does.
If light naturally wants to burst out in random directions at random wavelengths, what physical force could possibly compel trillions of light waves to suddenly align in perfect lockstep?
Well, to find that force, we have to travel back to 1917.
Okay, Einstein's era.
Yep. Long before anyone had the technology to build a physical laser, Albert Einstein was working out the theoretical physics of how light interacts with matter.
Right.
He is the one who figured out the stimulated emission part of our acronym, the S and E in laser.
Okay, I was wondering when we get to the acronym.
So to follow Einstein's logic, we need to understand a foundational rule about how atoms behave. An atom can absorb and hold energy, but it cannot just hold any random amount. It can only hold energy at very specific fixed levels.
I usually picture that like the rungs on a ladder.
Oh, that's a great visual.
Like you can stand firmly on the first rung, or you can climb up to the second rung, but you can't just, hover in the empty air between the rungs. The energy levels are discrete.
That analogy works perfectly for the energy states. When an atom absorbs some form of outside energy like heat or light, one of its electrons makes a quantum leap up to a higher rung on that ladder.
Okay, makes sense.
When the atom is sitting in that elevated state, physicists call it an excited atom.
So excited just means the atom is energized. It absorbed some juice from its environment and bumped up a rung.
Exactly. But atoms are inherently lazy.
Really?
Yeah, they do not want to hold on to that extra energy forever. Nature always prefers stability and balance. So eventually, that excited atom is going to drop back down to its original rung.
And it has to put that energy somewhere.
Right. And when it falls, it has to get rid of that borrowed energy. It releases it by spitting out a tiny single packet of light, which is known as a photon.
A photon. Okay, so the atom gets excited, jumps up the ladder, eventually gets tired of holding the energy, drops back down, and spits out a photon of light to balance its ledger.
That's exactly it. And this process is happening all around us all the time. It's called spontaneous emission.
Okay, spontaneous.
It is the exact mechanism making a neon sign glow on a diner window. Electricity excites the neon atoms, and then they drop back down, spontaneously emitting photons. But they do this whenever they please.
Right.
Randomly, in all directions.
Hold on, let me push back on this.
Sure.
If the atom naturally wants to drop to a lower energy state anyway, and it's doing so randomly, why wouldn't hitting it with more energy just add to the chaos? If the goal is a disciplined army, how did Einstein use these totally random, unpredictable atomic drops to create perfect order?
That is the exact paradox Einstein solved. He theorized that spontaneous random emission isn't the only way an atom can release its photon.
Oh.
There is a second, highly coordinated method. Think about a pair of acoustic tuning forks.
Okay.
If you have two tuning forks pitched to the exact same note and you strike the first one so it rings out, bringing it near the second one will cause the second fork to start vibrating and ringing in perfect sympathy.
Right. The sound waves from the first stimulate the second.
Because they share the exact same frequency, the energy transfers perfectly.
Yeah, I've seen that in music class.
Einstein realized atoms operate on a similar principle of resonance. If an atom is already sitting up on that higher rung, it's already excited, and a photon with the exact right energy happens to pass by, that passing photon acts like the struck tuning fork.
Oh, wow.
It literally tickles the excited atom, stimulating it into dropping down the ladder early.
It forces the atom to give up its stored energy right at that exact moment.
Yes. And crucially, because it was triggered by resonance, the new photon that the atom emits isn't random. It comes out as a flawless, perfect twin of the passing photon that triggered it.
A twin.
Same exact color, traveling in the exact same direction, and cresting and dipping perfectly in step.
Unbelievable.
This is stimulated emission. The passing photon stimulated the atom to emit its own matching photon.
Here's where it gets really interesting, though.
Yeah.
Because you started with one passing photon, but now you have two identical photons traveling side by side, totally coherent.
Exactly.
And if those two twins pass by two other excited atoms,
They stimulate those atoms to drop their energy. Now you have 4 identical coherent photons.
Right.
Those 4 sweep past more atoms and become 8, and 8 become 16.
It's a cascading domino effect.
Right.
Which brings us to the amplification part of the acronym, right? The A in laser.
You got it.
You are amplifying the amount of light by triggering this avalanche of stimulated twins. You're building that massive flood of photons that are all marching in perfect lockstep.
You are amplifying light by the stimulated emission of radiation. And the word radiation in this context just refers to the radiating light waves.
Laser.
Laser. The beautiful mechanics of the acronym are fully revealed.
That is so cool.
However, understanding the physics on a chalkboard is very different from building a device that can trap light in atoms and actually force them to do this.
Yeah, I can imagine.
Einstein published this math in 1917, but it took over 4 decades for engineers to construct a physical chamber that could execute the theory.
Right, because knowing how the dominoes fall is great, but building a track that forces them to fall infinitely without losing momentum, that is an entirely different engineering challenge.
Totally.
How did they finally build the machine in the real world?
Well, to manufacture a working laser beam, you have to execute 2 major physical tricks. First, you need a substantial population of atoms, and you need the vast majority of them to be excited and sitting on that top rung, ready to be stimulated.
Okay.
Physicists refer to this unnatural state as a population inversion.
A population inversion. I assume that's because in a normal population of atoms, most are just chilling at the bottom rung.
Right, they prefer being lazy.
So you have to invert the natural order, so the majority are holding extra energy, creating this target-rich environment for a passing photon to stimulate.
Exactly. And to force that inversion, you have to pump an immense amount of energy into whatever material you are using. You might blast it with high-voltage electricity or bombard it with a tremendously bright, intense flash of ordinary light.
Just giving them a ton of juice.
Yes. This aggressive pumping shoves the atoms up the ladder. That achieves your inversion.
Okay, what's the second trick?
The second trick is managing the photons once they start replicating. You need to give them a space to build up their numbers exponentially. You accomplish this by placing 2 precisely aligned mirrors facing each other, sandwiching your excited atoms in the middle.
So it functions almost like an optical echo chamber.
Oh, that's a fantastic description.
Instead of a sound wave bouncing off canyon walls and slowly dying out, the light is trapped. It bounces back and forth between those 2 mirrors, sweeping through the population of excited atoms over and over.
Yep.
With every single pass, it triggers more and more twins, amplifying the intensity until you have this overwhelming, dense concentration of coherent light.
An optical echo chamber is exactly it. The light sweeps back and forth, organizing more and more atoms into the marching army. But a perfectly sealed chamber of light is useless to us if we can't extract the beam.
Oh, right. It would just stay trapped forever.
Exactly. So the final elegant detail of the machine involved those mirrors. One mirror is 100% reflective, but the mirror on the opposite end is engineered to be slightly less than perfect.
It's intentionally flawed so it doesn't reflect everything.
Right. It might reflect, say, 99% of the light, but it allows a tiny 1% fraction to leak through the glass. As that intense, perfectly coordinated avalanche of photons aggressively bounces back and forth, a thin, sustained sliver of it escapes through that imperfect mirror.
Wow.
And that highly disciplined stream of pure, coherent light is the laser beam.
Which brings us to the actual physical birth of the laser.
Yeah.
The person who finally solved this engineering puzzle and built the first working prototype was an American physicist named Theodore Maiman back in 1960.
Right, and Theodore Maiman constructed his device by housing his atoms in a small, solid, cylindrical rod of synthetic ruby.
Or ruby.
Yeah. He wrapped a coiled flash lamp around the ruby rod. When he fired the lamp, the intense burst of light pumped the ruby atoms into that population inversion.
Okay, the first trick.
He had silvered the ends of the ruby to act as his mirrors, and out of one end emerged the world's first concentrated beam of pure red laser light.
It's just a gorgeous visual, isn't it? This glowing synthetic ruby crystal firing a perfectly straight beam of crimson light across a laboratory.
It really is.
But what I find so incredibly funny about this milestone is the broader historical reaction to it at the time.
Oh, yeah. If we connect this to the bigger picture of mid-century science, the reaction is deeply ironic.
Yeah.
When Maiman unveiled this working laser to the press and the scientific community in 1960, they were profoundly underwhelmed. There was actually a running joke at the time that Maiman's laser was a solution looking for a problem.
Meaning, congratulations on your neat little glowing ruby, Ted, but what on earth is anyone supposed to actually do with this?
Exactly. It was viewed as a highly sophisticated parlor trick, like an elegant demonstration of quantum physics that had absolutely no practical utility for everyday human life.
Which has to rank as one of the most spectacularly short-sighted judgments in the history of technology.
Oh, without a doubt.
They had absolutely no idea that this useless gadget was going to fundamentally rewrite modern civilization.
The ubiquity of the laser today really stems from a crucial realization engineers made shortly after Maiman's success.
Which was?
The acronym LASER only requires atoms. It dictates nothing about ruby atoms specifically.
Of course.
You can achieve a population inversion in countless different materials. For example, instead of a solid crystal, you can use a tube of mixed gases. For decades, the bright red beam scanning barcodes at your local supermarket checkout was generated by a helium neon gas laser.
The classic glass window at the grocery counter. We all remember that glow. But the true explosion in how we use lasers came when we figured out how to shrink them down, right?
Yes, the revolution really arrived with semiconductor lasers, commonly called laser diodes. Instead of giant glass tubes or synthetic crystals requiring massive flash lamps, engineers figured out how to create the echo chamber inside a microscopic chip of silicon-like material.
That's wild.
These laser diodes are roughly the size of a single grain of rice. Furthermore, they don't need external light to pump the atoms. They generate laser light directly from a tiny trickle of electrical current.
So a component the size of a grain of rice that costs pennies to manufacture is what allows a video game console to read the microscopic bumps on a disc, or a computer mouse to track movement across a desk.
Yes.
But the impact goes so far beyond consumer electronics. Let's talk about the internet. You mentioned fiber optic cables earlier. Why is a laser absolutely necessary to send internet data across an ocean? Why couldn't we just pulse a really bright LED light down a glass tube?
Because if you pumped ordinary light down a transatlantic cable, it would fail completely. Remember our chaotic train station crowd?
Oh, right.
Ordinary light is messy. It spreads out, it bounces at random angles, and the different wavelengths travel at slightly different speeds through glass. If you pulsed a complex internet signal using ordinary light, the data would smear and degrade into absolute static before it traveled even a few miles.
The signal would blur together because the light waves aren't coherent.
Exactly. But laser light is the disciplined army. It is a single wavelength, entirely coherent, traveling in a tight beam.
Right.
When we pulse laser light down a hair-thin fiber optic cable, it bounces cleanly along the interior of the glass through a process called total internal reflection. The waves stay tightly packed and perfectly synchronized.
Wow.
That purity is the only reason we can shoot terabytes of data from New York to London in milliseconds without the information degrading.
That cohesion is also what makes lasers so devastatingly effective in heavy industry and medicine, isn't it?
Oh, absolutely.
Because the light waves don't spread out. You can run a laser through a magnifying lens and focus all of that energy down to a microscopic pinpoint. If you do that with ordinary light, you might get enough heat to start a campfire.
Right.
But if you do it with a high-powered industrial laser, you're concentrating thousands of watts into an area the size of a pinhead. The localized heat is so intense it instantly vaporizes thick steel plates in car factories.
Or, on a much more delicate scale, surgeons utilize that exact same pinpoint focus.
Right, like we mentioned earlier.
They use specialized lasers to slice through tissue, instantly cauterizing and sealing blood vessels as they go, or to painlessly ablate and reshape the microscopic curves of the human cornea during eye surgery. You are wielding energy with sub-millimeter precision.
And beyond industry and medicine, lasers have become our ultimate ruler for measuring the universe, haven't they? Like the LIGO Observatory, which detects gravitational waves, relies entirely on the laser's purity.
Yes. Gravitational waves are literal ripples in the fabric of space and time, caused by massive cosmic events like black holes colliding.
Mind-blowing stuff on its own.
When those ripples pass through Earth, they stretch and squeeze our planet by amounts vastly smaller than the width of an atomic nucleus. You cannot measure a change that unimaginably small with physical tools.
So how do they do it?
Instead, physicists fire kilometers-long laser beams down vacuum tubes.
Because the laser is a single pure wavelength marching in perfect lockstep. It acts as an unchangeable microscopic ruler.
Yes.
If space itself stretches even a fraction of an atom, the laser's journey takes slightly longer, the lockstep waves shift out of alignment, and the scientists can detect the ripple.
You could only ever achieve a measurement that precise with light that is completely ordered and coherent.
So what does this all mean? When you take a step back and survey the trajectory of this technology, it is staggering.
It really is.
In 1960, a massive room full of high-voltage laboratory equipment, precision mirrors, and synthetic ruby rods was required to generate a single beam of coherent light. Today, that exact same quantum manipulation has been shrunk down into a throwaway component we scatter through the world like confetti.
It is the ultimate quiet triumph of theoretical science, from a laboratory curiosity mocked as a solution looking for a problem, to the invisible thread sewing global communication, manufacturing, and modern medicine together. And to summarize the journey, everything we've unpacked today traces back to one elegant physical reality: light in lockstep. An ordinary lamp emits a chaotic, desperate jumble of energy. A laser persuades countless atoms to sing their energy out in perfect, synchronized unison.
Which brings us right back to you, listening to this deep dive. Whether you are using a plastic pointer to entertain a pet, receiving sight-saving surgery, or just relying on the undersea glass cables delivering this very audio to your device right now, you are interacting directly with an abstract physics equation sketched out in 1917.
Incredible, isn't it?
Einstein saw the resonance, Maiman built the ruby trap, and now manipulating quantum states is just a mundane part of your daily routine.
And this raises an important question, something for you to mull over as you go about the rest of your day.
Let's hear it.
Since the laser was once completely dismissed by the brightest minds of the 1960s as a useless parlor trick, what incredibly dense, seemingly pointless theoretical physics equations being fiercely debated in obscure university laboratories today are secretly the blueprints for the throwaway, everyday gadgets of our future?
What a fantastic thought to end on. The chaotic crowd transforming into a synchronized army, all thanks to some carefully tickled atoms. Thank you so much for joining us on this deep dive into the hidden world of lasers, and as always, keep asking questions and stay curious.